So good morning, welcome back to our power electronics course. Today I continue to the next part on analysis method, and this part is called periodic steady state. So first you need to understand the steady state term and also then the periodic. What does this mean? Mathematically, we have relationship between voltage and current for some storage element. For example, in here, for an inductor, the voltage across an inductor L. So the voltage here VL equal to L times derivative of current across the inductor, and we can have relations. We can have the condition that for the steady state, periodic steady state, the average value of this derivative term equal to 0. So why it's always the case? Okay. So I'm going to explain why. Last 2 weeks, you already learned the simulation of filter, right? If we have a circuit like this, let's say we have VH. So VH can be any periodic voltage equivalent. Then you have filter with inductor and capacitor, and you have load R, like this, so L, C, R. And when we simulate it based on differential equation that we can derive from this circuit, right? And suppose that VH is pulse is a rectangle. Sometimes we call square wave, but it's not always square. It depends on the scale of the time. Let's say the pulse, it's like a rectangle waveform, and then you have the output voltage here, which has the form of periodic as well. Okay, it has periodic waveform. And that waveform, if you look at the steady state, so I'm going to show a simulation here. Look at the bottom one, ignore the top one. I think actually, I can change it to be the same actually, because I use this one 50% and this one is 75%. So if I also use 50%, then these two, the output should be the same. So I'm going to show this one. Where is the other one? Here. Okay. Can I zoom in? This one? I zoom from here to here. Well, okay, so first try to understand the term periodic steady state. If you look at from the beginning, we call it transient. It transits from 0 to a certain value. But before it converges, if you look at the black one, you can see that it converges to a constant here, right? But the blue one, or the green one, not convert to a constant, but it's steady. It's steady as a waveform. It's not sine wave. It doesn't have to be sine wave, but it's steady at the steady state. So, as time tends to infinity, you get the output steady. The waveform repeat itself all the time, right? So at the beginning, it's not steady yet. And you know, from 0 to only 0.05 seconds. What if after 1 second, 2 seconds, 3 seconds, let's say you operate your electronic device for a period of time, let's say 1 hour, 2 hours, so of course you only care from this part, you don't care during the transient, around 0 to 1 second, for example, right? So periodic steady state, we only consider when the output is steady. Okay, and so why the average value of derivative of periodic steady state is 0? So you look at the graph, the curve again. If I want to write down the let's say the green one is the waveform of current, okay? Yeah. Let's say the waveform of current is like this. Yeah, actually from this equation we say the V out is the voltage on a resistor, but the current on the resistor is just voltage divided by R. So the waveform of current is just the same as voltage here. I mean voltage waveform. So suppose I have suppose I have voltage of a current waveform at the steady states like that, like this. So I have the average value. So I only consider the periodic steady state. It's not so good. Okay. Maybe just one period. It's better just one period. Yeah. It can be triangle like this. I draw now. Can be triangle. Okay. So this value, the average value here, I would call it just like, I put the this symbol to be average value at here. Average value means the area on the above the mean value, the average value, and the area under the average value are the same, right? So then I write down the current, the function of current equal to its average plus some periodic function. Okay, periodic of time. I mean, so if I write down like this, then if I draw only the periodic function here, it would have average value at 0, right? This periodic of t, like this. Do you agree? Because if I add this one with this average value, it's going to move up here, right? Right. Now let me take the time derivative of the current. This one 0, right? And then plus derivative of this periodic, I think maybe there's no t here. Yeah. Right? Then, well, if you have a periodic function like this and you take time derivative, it's still periodic because the tangent line here has this slope, then the tangent line here still have the same slope, right? So it's still periodic, this one, still periodic. And the most important fact is that this periodic function also has 0 average value. That's why when we apply the average value to this term, and we have this average value of this periodic function, it must be 0, because when we apply average value, it means we take the integral for a period, right? Okay. Okay, now you know one property, which is for periodic function, for periodic steady state, the average value of the voltage on inductor is 0. Okay. And then, yeah, so from this fact, we can do some analysis for the circuit. Suppose we have a circuit like this. We have diode and inductor and resistor. We don't have capacitor, so we just ignore it. Then we analyze using periodic steady state. First, we apply Kirchhoff voltage law on this loop. So we have voltage. So we put the terminal positive, negative like this. So you have positive of the source, and then this one minus 2 plus, you assume it to be positive, and then this one plus 2 minus, then it must be negative. Here plus 2 minus, also negative. So from this analysis, we can see that because from periodic steady state property, the average value of sine wave is always 0. This is true, right? Because area above area under the sine curve. Okay, I'm here. Look at this one. Look at this one. Look at this one, the blue one. The area here and area here are equal, but one plus and another one is minus. So it's always 0. And periodic steady state of voltage across inductor also 0. Then we can find that the average value of V0 here is always 0 too, right? So what does this imply? It implies that if diode were always on and V0, average value of V0 is 0, then V0 has negative value, right? If it has negative value, then current also has negative value, right? Because current on V0 or current on the resistor, right, always have the same sign as V0. Current here, I0. Okay? So the assumption that diode is always on is wrong. This is what it means. We are trying to, first we make assumption on the state of diode, and then we do analysis using periodic steady state, and then we figure out that current can have negative value. Then that's not true. It means the assumption that diode is always on is wrong, right? Then we can conclude that diode must turn off during part of the cycle. Okay. So actually, diode will start to turn off when the current drop to 0. Current cannot go to negative, just like that, right? Currents like this, when it go to 0, then diode turn off, and current keep 0 like this. Okay. Now let's take a look at half-wave rectifier, and we try some analysis. So here, oh, let me change. Okay, I will come back later. So the difference between this circuit and the previous one is that we use the freewheeling diode. This one is called freewheeling diode. So why do we want to use this one? It is because if we only have one diode, and because the energy stored in inductor will release when this one become negative. Okay? It still suck the current. I mean, even though the potential from this side is larger, this one it's like a spinning magnetic flux spinning. It has momentum. It has kinetic energy. It still suck current on the opposite side from the source. That's why voltage become negative like this. Okay. This is VH. VH means you use terminal here and terminal here. VH. And because VH has some negative part here, in negative, here is positive. Okay, the black, the dot, the solid, the biggest solid line. If you find the average, you have this area and you minus this area. I mean, it's like you have some low voltage due to this part. So if we try to eliminate that part like this, we need to use this freewheeling diode. So why this freewheeling diode can help? It can help because when the source have negative voltage and this one still keeps sucking current from this side, but because this one has low voltage, then here instead it suck current from this way. Okay, so if it suck from this way, the voltage here is not negative, instead it's just zero, because this becomes just a conductor with assumably zero resistance. Okay. You have any question? Yeah, in power electronic circuit is not easy as a simple circuit because we have a switching in there. It's not so easy, but well, you need to know some principles. Then this is the summary of what happens. D2, which is this one, D2 clamps so that VH never goes negative, right? Yeah. Using method of assumed state, D1 conducts when the sine wave is positive, sine wave from the source here. So when this one positive, this one conduct current to go this way, right? This loop. When D2 conduct when the sine wave is negative. D2 conduct when sine wave negative. So this one, the current on the load just run this loop. Okay. Is there any question? Yeah, try to ask. So you already understand everything. Okay, I will continue if there's no question. So from here we can find average value of voltage VH, VH in here. So why do we care VH around here? Because this is the actual input to this dynamic system. We can derive the differential equation for a system with these elements, and then the input voltage would be around here, right? So VH somehow it's equivalent of everything from here, right? You can have source in a certain waveform, and then you have bridge of diodes, but finally you just have voltage around here, and you want to analyze using modeling and simulation, you just start from here. Okay, you analyze to get VH first. What is the waveform of VH? Like here, it's a half wave of sine wave, right? So this waveform is the input of the differential equation for inductor and resistor. So let's find average value of V out. Average value of V out is the same as average value of VH. Why? Because average value of voltage here is 0, periodic steady state, right? So if you want to find the voltage on the load, on your load, you just find the average value of VH. That's right. Okay. So average value is just integral from for integral in one period, but from here to here you just have 0 value of the function. Then you just need to take integral from here to here, but here you still divide it by 2 pi, right? 1 over period, integral from 0 to the period. Okay? Sela, do you understand this? How can I get this? Okay.
This is just the integration from 0 to pi of the function, like when we look at the graph from 0 to pi, we have the equation of Vs sine free d free.
And how about this one?
Yes, 2 pi.
What about this? This one just 0, right? Because VH here is 0. Integral of 0 constant, and constant evaluated here and constant evaluated here, just same, still constant, right? Okay. Next. Yeah, this one a little bit complicated. Actually, this is the theory that prove that the output of voltage here at steady state is still periodic, because we can do some analysis using Fourier series. First, we make this one as a Fourier series, and using a property of linear system or using transfer function, but I don't think you can understand for now. I will skip this. If you are familiar with control system, with transfer function, frequency response, and then you can understand this, but I think still too far from you. Okay, so far the technique that you have seen, there are 3 main points. First, method of assumed states. Second, some important property for the periodic steady state, and the third one, you use the equivalent source replacement. Like here, like I mentioned before, about VH. So VH is some kind of equivalent voltage. You ignore all the complicated circuit as long as you know that the voltage at here just before it supply to your filter, then you just use equivalent voltage at that terminal. Okay, just like this. So in some sense you make analysis 2 stage. First stage, using all the method that you have learned to get that what is the waveform at here, and after then from here you can use a linear theory circuit. There's no more switching in here, but you have this kind of waveform of input. Okay, I'm going to show another way of analysis, which is to derive the differential equation. Once you make assumption, now once you figure out which switch is turned on, which switch is turned off. Okay. So and for this method also has another advantage, that if you can make analysis that which switch should be turned on or which switch should be turned off in a certain period of time. Okay. So yeah, let's go through step by step. This method is a little bit more difficult than the previous one, actually. But anyway, you should get to know some methods. Okay. Well, first let me explain the notation and the symbol here. This one is symbol of current source. Current source means you have a device here that can control such a way that current that flows from here to here always I, capital I. Okay. No matter what you do with the circuit at this part, this try to generate current I. This one is battery with electromotive force E. Yes, with just voltage E. This one capacitor. This one is control switch, fully controlled switch. You can turn it on and turn it off. This one just diode. Okay. Now let's look at the sequence 1. It's called free wheel sequence. When D is on and K is off. D, this one. Okay. K, this one. When this one off, so you have open circuit in here. Because this one is on, you have closed circuit in here. Right? And what happened? Look at so here the what we are interested in, or what we should we should make it as variable for differential equation. There are voltage at capacitor and current on inductor, because these two are storage elements. Whenever you derive this equation from electrical circuit, variable on storage element will become a variable for the differential equation. Okay. Okay, so let's take a look at the voltage on capacitor first. When this one is on, this one there's no voltage drop in here, so voltage at capacitor here just same as voltage of battery here. So V equal to E, right? It's just parallel, right? And VK also same as V because just parallel. How about current I on inductor? Because here is open circuit, I is 0. So it's easy to derive the equation for this case. Okay. How to do to create this sequence? we have to turn on, we have to turn K on. Right? Actually, you can leave it as long as you want, but once you want to quit this sequence, you need to do something, which is to control the switch K to be on. And is it possible? Yeah, let's check with step 3. When you turn this one on, what happened? D is still on. Okay, so assume that D is still on, and is it possible? It violates any condition or not? D on, K on. Is there any short circuit or over voltage? Let's take a look. This one in parallel, then this one L, right? So it seems okay. Then find the order of new operating sequence. Order here means order of differential equation. Okay. So how you can find it? Again, we need to find relationship of between voltage and the given parameters such as voltage source and current source. So first you can see the circuit here, voltage here, V here, and E still parallel, so this one checked, V equal to E. How about here? Relationship between current and voltage across inductor. Okay, voltage on capacitor here and voltage on inductor here is the same. Okay. So, which is the same as E, and voltage on inductor L di over dt, right? So you have differential equation, and if you look at D, it's just first order differential equation. Okay, first order. Okay. So let's take a look. This sequence can last forever or it can change. Yeah. Look at here. Current here always I. Always I. When D is still on, current here can be at the initial state, the current here is I itself, but when the current from inductor start to flow, so you also have IL here. So as long as this one increase, this one decrease, because the sum of these two is I here. Oh, sorry, capital I. The sum of ID and I, lowercase I, just call it IL. The sum between ID and IL is I. Okay. So this one start to increase, this one start to decrease. Right? It increase until this one IL is the same as I. So this current source just suck the current from the inductor only. Okay, I mean from this brand only, maybe capacitor also, current can also come from here or whatever. But the most important thing is that once current I from here, from this branch equal to I here, this one turn off. ID turn off. Okay, so it means this operating sequence will end when IL equal to I. So now we analyze the sequence that D is off. So here is open circuit, K is on, K is still on, so here is still on. And let's derive equation, differential equation. From here, Kirchhoff current law, you have current I here, and you have I from inductor and also I from capacitor. I from inductor is just I like this, and from capacitor you have derivative of charge with respect to time. Okay, C time V is charge, and you have relationship between V here and the current here, V equal to LdI over T, and we make substitution here to just to get one variable I, then you have second order differential equation. Okay, yes, second order. If you have second order like this, what is solution of I? Can you immediately see the solution, the form of solution? Second order differential equation. If you look at the characteristic equation, LC lambda square plus 1 equal to 0, then lambda equal to what? Like this? Anything missing? Anything missing here? Minus? But actually minus in here. Minus 1 inside. So you have complex number. If you have complex number, what is the solution of differential equation? It's exponential or trigonometry? If characteristic root is complex number, complex conjugate, 1 plus 1 minus, always. If complex, if polynomial function have complex root, the complex always has pair, conjugate. Then you have trigonometric function as solution. So if I is, let's say I is sine wave, what is voltage? Because I and current and voltage, the relationship between current and voltage is just time derivative. Is I is sine wave, voltage is cosine. Yeah, one sine, one cosine, right? If one sine is cosine, you plot I versus voltage in here, one cosine, one sine, you have some coefficient. So the waveform should be ellipse. Right? Just say I equal to A sine omega t and V equal to B cosine omega t. And if you write I over A equal to sine omega t, V over B equal to cosine omega t, then you square this plus square this equal to 1. So in the relationship, or we can say the phase plane on I and V, it's some kind of ellipse. Okay, maybe 0 around here, depends on this plus some constant C, this one plus some constant D. So I would write I minus C here, I would write B minus D here. So ellipse might have center here, right? So when you have a second order differential equation like this, and the solution is trigonometric, then the relationship between one variable and its derivative will be ellipse. Okay. Yeah, you will see why this is important. I did not explain. How about the relationship between for the first order? yeah, again, V and I, the relationship between V and I is their derivative, time derivative. But in this case, yeah, in this case, the first order, the equation can be, yeah, the solution is always what? First order solution can be exponential or can be some constant, right? Let's say I have equation di over dt plus ai equal to v. So look at characteristic equation. We have lambda plus a equal to 0. So lambda equal to minus a. Then the homogeneous solution would be e to the minus a t, right? So what I want you to observe is that if I have current is just some constant e to the minus a t, let's say plus some other c1, c2, and then v is time derivative of I, then I can have what? I can have some other constant called c3 e minus a t as well, right? So can you find that the relationship between I and V just line? Can you find a relationship like that between V and I? Because here I can write I minus C2 over C1 equal to E minus AT, right? And this one V is just V over C3 equal to. So if we compare these two, you can have a relationship. V and I is just 9. Okay? I mean, if you want to plot V and I together, it's just some line. Okay. And next, sequence 4. In this case, D is still off, and we switch K to be off. Right? So you have open circuit here, open circuit here. Then current here becomes 0, and current I here is the same as current I pass through capacitor here. So that you have this relationship between I and voltage of the capacitor. And voltage VK here is parallel with the voltage V here. Okay, and parallel with E. Oh, sorry, not E anymore, because you have this one. You have this voltage here. Okay, and the voltage at D, we need to check voltage at D, because if you find out voltage at D is negative, then it cannot. No, if voltage D is positive, then it cannot. Look, D from here to here. Okay, if you use plus here and minus here, if VD is positive, it's true, right? Because current cannot go this way. And okay, VD equal to V minus E. Let's take a look at the terminal here, plus minus, and here there's plus, there minus, plus minus, and here, oh, plus minus here, like this. Try to write down using Kirchhoff voltage law. So E minus V plus VD equal to 0. Then VD equal to V minus E. Okay, so I said incorrectly here because if we use plus terminal here and minus terminal here like this. So if you find voltage VD positive, that's not true. I mean that circle it cannot happen, because if potential here higher than potential here, current must flow like this, and it must turn on. It cannot turn off. In order to have it turn off, you have negative voltage, right? You need to have negative voltage VD. Well, here is the relationship between V and I from the equation above. I will explain it step by step from the equation before. But before I continue, let's take a break for 5 minutes, because you want to have some break maybe.